Today we consider one variable optimization model maximizing the profit of raising a peak. Please read the section 1.1 from the textbook or the material for the lecture 1 posted in the Blackboard. So we're going to state the problem of raising a peak, then build up a mathematical model, then use calculus, the derivative, to solve the model, and then interpret the solution. Here is the problem. A pig weighing 200 pounds gains B pounds per day and costs 45 cents a day to keep. The market price for pigs is 65 cents per pound, but it's falling all cents per day. When should the pig be sold? Here's the procedure to build a mathematical model. The step 1 is very important to introduce the variables. So to use mathematics, we need the variables. No variables, no mathematics. If we read through the problem carefully, you will see the day, the time is the important variable. So we introduce the t for the time. The weight of the pig is another important variable. We denote by W. And the price is another important variable in the problem. Then the cost to keep the pig. Of course, the revenue by selling the pig denoted by the order. And finally, we want to see what is the profit. Next, when we have the problem, we make many assumptions. So it's very important to identify the assumptions from the problems. So we wrote down the assumption by using the mathematical equations. The pig weighing 200 pounds gain B pounds per day. This is one assumption in the problem. Mathematically means the weight W is equal to 200 plus the weight gain per day, B times T. From this statement, we have another assumption. Costs 45% per day to keep. So we have another equation. Mathematically means the cost C is equal to 0.45 times the time T. Another assumption in the problem is the price for the pigs is 65% per pound, but it's falling all cents per day. In mathematics, this tells the price P equal to 0.65, 65 cents per pound, falling all cents per day, which means minus where 0.01 is converted from the cents to the dollars. So that's why we have the coefficients 0.01 all cents per day, so times the time T. So those are the three assumptions in the problems. Then we have three equations for each for the assumptions. Then we write down the equations. Then the profit, the P is equal to the revenue minus the cost. And the revenue is equal to the weight. Revenue is by selling the pig, so it's equal to the weight times the price P. The P times W, the revenue minus C. Then we plug these equations, these three equations, plug into. Then we have a concrete mathematical equations for the profit, and this is the mathematical models of these problems, which is the quadratic equations in time t. Next, we solve the model. Model is to maximize the profit. So to get some iterations, we plot these functions p against time t. From this graph, you can see at some time the profit reaches its maximum. And then let's see what kind of mathematical theory we can use to find the maximum. If we recall the calculus 1, we can use the derivatives. You can see it's the maximum. The tangent line. Oh, not good. The tangent line to the maximum point is horizontal, which means the slope is 0. Slope means the derivative, so the derivative is equal to 0. So to find the maximum of these perfect functions, we compute the derivatives. We can use the Potter rule to calculate the derivative. So if we go back to the function, you see, so the derivative, we're using the products to calculate derivatives. The product rule of the derivative. Okay, then we simplify. Then we get the derivative of these perfect functions. Particularly when b equal to 5 or is 1, then the derivative function is simplified. Then we set the derivative equal to 0, and then we find the maximum of the profit is achieved when t equal to 8. And the maximum profit is equal to the value of the perfect functions when t equal to 8. So we plug 8 for t into the original perfect functions, then calculate, then we get this nullus. Let's have some discussion about the weight growth rate and the price. In these problems, weight growth rate B is supposed to be a constant, but actually it can be a function of time t. For example, B can be equal to 5 minus t over 20. So let's see if this kind of functions for the B make sense. If we plot it, the t, and then b. When t equal to 0 is 5. When t equal to 100, the b is 0. So the graph of this linear function is a straight line going through these 2 points. I think this makes sense. When the 100 days later, the peak is getting older and older and no longer gain the weight. So which means 100 days later, the growth rate is zeros. We can also propose another functions like this exponential. If we plot it, the growth rate exponentially decay over the time. When t equal to 0, b is 5. So the negative 10t in the power. So this exponential decay functions. Also, this makes sense because when the peak getting older and older, then the growth rate is getting smaller and smaller eventually, and no longer gain the weight. Again, the falling price order is a constant, but again can be a constant of can be a function of time t. For example, the falling price probably increase all the time linearly, so the 1 cent plus 0.1 t. Another functions can be such as saturated functions if we plot these functions. So when t equal to 0 is 1, so 1 cent. When t approaches infinity, e to the negative approaches 0, so this frequency approaches 2. So the graph of this function like this. So which means the falling price increasing over the time, but at the most just 2 cents. I think this second function could be making more sense than the first ones. Of course, you can propose many other functions for b and r. It really depends on the real situations. So you can do lots of work about what could be the best functions for the r and the t. So that's why we need to collect the data, and the data will tell us what could be the good functions for r and b's. Okay, so that's all for today's.